ground images to overhead reference. And then if I have time, I'll get to the second topic, which is ground view matching 2D ground images 2.5D reference, not just 2D reference, but 3D reference or 2.5D reference. I won't definitely have time for the third topic. So one reason why I was interested in this problem is because of this image. So there was a hiker who was lost in the Los Angeles area mountains, and he took a picture from his cell phone, and he just had a little bit of battery charge left on his cell phone. So he sent the picture to his friends, he texted it to his friends, and they gave it to the police. And then there are lots of people who do geocoding of images as a hobby. So those people, the police spread that image around, and the people who do geocoding were able to match this image to satellite image and locate him. And from there, the police were able to rescue him, right? So this is a very nice example of being able to locate yourself just from an image. Of course, this problem of image-based geolocalization or visual geolocalization has many applications. There's applications in autonomous vehicles and robotics, for augmented reality, for 3D modeling, for geotagging images. So it has lots of applications. And what I'm going to focus on is matching, locating yourself by matching the ground image to a reference database. And you could think of that problem having three different flavors. The first flavor is that it is like you have images which you've taken at the ground, and you're matching ground images, but they've been taken across time. And now you're trying to match to them. So the challenge here is you're matching images, maybe from different viewpoints but from the ground, but taken at different times, so the world looks different. The second way to do it is cross view, which is the focus of this talk, where you have images taken from the ground, and you're trying to match them to aerial or satellite reference. And then the third way is you're matching your ground images to maps or LiDAR or some other modalities, a cross-modal. So in this talk, I'm going to just focus in the middle one, cross-view. And so essentially, you're given an image, could be a street view image or any ground image, and you're trying to match it to these satellite images. We call them in the talk bird's eye view images, sometimes I call them aerial images, but really the satellite images which have been taken from overhead. And you're trying to locate yourself by matching to these. And so the challenge of this problem is there's an extreme viewpoint change between the ground and aerial images. And then also the ground image has a limited field of view. The bird's eye view image and satellite images have a very large field of view, but this has a very limited field of view. To solve this problem, you can use many different cues. And it really depends where you are. If you were where we are outside this hotel, you may use this method of matching the ground image to skylines. You detect the skyline in the ground image, you detect the skyline in the 3D map which you may have, say from LiDAR or from a train map, and you may use that. Or if you were in a suburban area, you may be matching to the building outlines, right? Or in a more area where you have varied terrain, you may be using semantic labels. So you can have a variety of cues which you could use to solve this problem. And really, what solution you use will depend on where you are. The solution which you use in an urban area won't really work when you're in Tucson looking at the desert and mountains on the side. In this talk also, the other part of the talk is more focused on more urban kind of imagery, right? The techniques I'm going to talk about have been tested more in urban kind of imagery and not so much on this rural desert kind of imagery. We have different techniques for those. And so there have been many data sets collected for this problem. I think you've heard some of them in the previous talk, CBUSA, CBACT. The first speaker was speaking of University of 1652, Vigor Chen, who's the organizer of this tutorial, and his student collected Vigor. recently there's CBCT, CB Globals. And many of these have been constructed by getting Street View images from Google Maps and satellite images from Google Maps. And there also have been many data sets like this collected for autonomous driving applications. If you right now, all these autonomous car companies drive around cities and build ground level maps and have to keep updating them. And that's how they locate their vehicles. If you could match the ground views to aerial maps, much easier to maintain. And so people have been working on this, and there are these data sets which people have been constructing for this autonomous driving application. To solve this problem, today in the age of neural networks and deep learning, when you're thinking about how to solve the problem, you have a query image, and you build a database of images that you had before. For the database of images, you know the geolocation, you know where those images were taken from, and the location and orientation. So you have your query image, you generate some kind of image representation. For your database of images, you also generate some kind of image representation and embedding. And now you're doing some kind of similarity search, right? And you'll get a list of candidates, and then you can do some refinement to get a refined list of candidates. And normally you have different ranking loss functions. So you could train with positive and negative pairs. So here you have, you're looking for images of Steph Curry. If it's not the image of Steph Curry, it would be a positive pair. An image of Klay Thompson would be a negative pair. And you can put these in this kind of pairwise loss functions, or you can combine them and make a triplet loss function. And many of the techniques have been using these as standard techniques for doing this. So one of the first papers to work on this cross-view matching using neural networks was the CVM net paper. It would take the images, the ground images, and the satellite images, have CNNs to build feature representations, and then it would build a global descriptor. And the global descriptor is based on NetBLAD. And NetBLAD was developed just for face recognition earlier in 2016. And it's basically a generalized trainable version of BLAD, where you're basically taking each patch and coming up with an aggregated descriptor for each patch. Basically saying this is the orientation of this patch and this is the average orientation of this patch and the magnitude. And so you take these local features, you have this global descriptor which you generate from these local features, and then you're matching these using the Siamese network or the triplet loss. One breakthrough which came in this field, which really advanced the results, was this technique called SAFA. And this was developed in 2019 by Shi et al., the group in Australia. What they did was the first idea they had was make the aerial image look more like the ground image, the ground panorama. So the way they did it was they did a polar transform. They take the aerial image, and they had this intuition that vertical lines in the ground image correspond to radial lines in the aerial image, and circular lines in the aerial image correspond to horizontal lines in the ground image. And so they did this polar transform based on these equations to take this aerial image to create a polar transformed aerial image. And then they do matching between these. So that was one of the key intuitions they had. They had another intuition, which was, okay, you take these ground images and polar transform aerial images, you run it through a CNN, but now instead of using the BLAD, they're trying to find which features are important. Because when you take the aerial image and warp it to the polar image, there are lots of features which won't match, or lots of parts of that which won't match the ground image because it's seeing different things. So what features are important? So they had this kind of max pooling operator to say these are the most distinctive features. And then they also encoded the relative positions of these features. And then so they were learning, okay, these are the most important features, that this is the relative position between them. And they had multiple of these modules. So if you know about transformers, this is the kind of thinking you do in transformers, but this is before you're using transformers, right? So still using CNN. And they also, in a subsequent paper, searched for orientation. So they didn't assume the orientation was known. And so they had this technique called dynamic similarity matching to also search for orientation. And essentially what they were doing was they would take this polar transform aerial image and they could rotate it and then match to the ground image to make sure this was the best matching one. And if your ground image was not a full panorama with a limited field of view, then they could also crop the polar transform image, the embeddings for it to correspond to that. And then they would do that, compute the embeddings, do the correlation, find the best correlation by shifting it, and then add that to the triplet loss, use that for the triplet loss. So they had a big jump in performance. You can see CVMNet on these data sets, CVUSA, CVACT, for rank 1 at field of view 360, they jumped from like 16% to 78%, right? So that was a big jump of performance. Of course, if you reduce the field of view to like 70 degrees, the performance was just about 8% at rank 1, right? But still, it was a big jump in performance from what was there before. Now, another data set which Chen over here and his student Zhu released was the VGAW data set. And one of their ideas was that the CVUSA and CVACT data sets were not really very realistic because there you had matching satellite image. The center of the satellite image matched the center of the panorama. And in a real world problem, that won't be true because you're trying to locate the image, you don't know where the center of it is, so you can't expect the area references to be there. So they had overlapping, what they did was they took the satellite images and made, tiled them, and they made overlapping tiles. So if the ground image, the center of the ground image lay in the center square of the satellite image, they call it a positive sample. And if it lay outside the center square, then they call it a semi-positive sample. So any ground image could potentially match to 4 images, 1 positive and 3 semi-positive. And they also had, they took the street view image and the aerial image, they ran it through the CNNs. They also used the SAFA block, but they added extra terms to their term. So there was a triplet loss, but they also said, okay, the ground view image should match to both the positive image with the semi-positive image. The match won't be as strong to the semi-positive image as the positive image. So we can have this IOU loss where the cosine similarity between the semi-positive and the positive should match to the ratio of the IOUs. And they also searched for the lat long. They assumed the orientation was known. They were just searching for lat long. And then they were able to show that on the VGAW data set, they had a much good jump, say for top 1, for from the SAFA technique. But still, again, for cross area, you train one area, try and test another area, the performance was still about 11%. So then transformers came in, a whole set of new techniques came up with transformers. And so just to introduce you, one of the earliest techniques of using transformers on vision was VIT, the vision transformer, where you take an image, you break it up into patches, you take each of these patches, you project them into an embedding, and then you run it through a transformer. And typically, at the end of the transformer, there's an MLP, and the first token of that is the CLS token, and that's used for classification. So in our group, we also worked on this using transformers. And what we did was we took the patch sizes, and then instead of using the class token, we took the last layer of tokens, and we reinterpreted them as a feature map. And then we would run a decoder to come up with an embedding for this image to match to it. And then not only did we do that, but we also borrowed the idea from the SAFA guys with the dynamic matching to have the sliding window correlation to match for orientation. But what we did was we took the triplet loss, which was there, and we multiplied it with an orientation weighted loss. So what we were doing was we not only have the triplet loss, but we are saying the triplet loss and is weighted by how well does the orientation correspond to ground truth orientation. And we use that to train. And we were able to show that we got a much higher performance than the previous transformer methods which were there on these CVUS and CVACT data sets. We jumped from say 94.08 to 94.89, and similarly, for CVACT. And similarly, we were able to solve for orientation also, not only use it for finding the top matching satellite for location, but also what should the orientation be. And on these data sets, using the full panorama, we could get within 2 degrees 93% of the time, and within 12 degrees 99% of the time. So then in 2023, actually I think it's CVPR 2023, there was a new paper which came out called Sample for Geo, which really improved performance a lot, and you'll see that. And they had 3 key innovations. The first innovation was that they used a convex model instead of transformers. And the advantage of using a convex model is that it can be used with images of different sizes. So when in transformers, when you train it, you've trained it with also precision embedding. And if you want to go to images of different sizes, it's problematic. If you use a CNN-based architecture, then it's easy to train with one set of images, but then use it on a different set. The other idea which they had was they sampled hard negatives. So what they did for sampling hard negatives was they had two ideas to it. So say you have this an image. This is an image, and it could match to these other images. So if there's an image which is very close in the training data to the original image, but not the right one, they said I'm going to use that to first train with. So they are nearest neighbor sampling with things which are wrong. Instead of using things which are far away, they were saying that's not going to help us so much. So let me use things which are not correct but are close to me and use that first. And they would train with the nearest neighbor sampling first. And after that, they would say, okay, I've done that for a bit. Now I'm going to look for those negative samples whose cosine similarity is close to mine, who are visually similar. And then I'll train with it. And so they would sample hard negatives that way. The second thing which they did was the third thing they did was they used a symmetric info C loss. So instead of using a triplet loss where you, in any error term, you had one positive and one negative, they said we'll have one positive, but we'll use all the negatives in a batch. And that can be seen over here. So say you have a set of query images and a set of reference images, you can put all the reference images as columns, put all the query images as rows, and for each one there's only one-to-one match between each query image and one reference image. There's one-to-one match, and all the others are negative, right? And you can do that both matching either way, either when you're matching from satellite to ground or from ground to satellite. And so you can do this loss both ways. That's why they call it symmetric, because you're doing it both ways. And they did it across rows and across columns. And they were able to get a big jump in performance. So for CVUSA, CVACT, they jumped up to 98.68, so much higher than the previous techniques, which are like 94, 95. And even for CVACT, they jumped up. And similarly, on the VGAW data set, they also jumped quite high. Even for cross area, the performance, jumped quite high, if you remember from the VGAW data sets. So this was like a very nice method, which really advanced the field. So all the techniques we've been speaking with so far have been projecting the aerial image or satellite image to look like the ground image by doing polar transformation, or they've not been doing anything at all. Like in the sample 4 Geo, they did not do anything at all. They said in their paper, if you do it, you may get a couple % more improvement, a small improvement still, but they didn't do it in their paper. But there's another set of techniques which people have been developing, which has actually started from the automotive, people working on autonomous cars. which is projecting the ground image to look like a bird's eye view image or an overhead image. And here's an example. Typically in these cars, you have lots of cameras looking all around, front, right, back, right, and left. And now you're trying to make this bird's eye view image over here. This is a semantic image where you're saying this is the road, these are other vehicles on the road, this is the pavement, things like that, right? So, and there have been a lot of papers on this. And if you could think of these papers, you can break them into two sets of papers. They're geometry-based papers and they're neural network-based papers. So you take the perspective view, geometry-based papers, the simplest thing you can do is just do a homography. You can assume you're looking at the ground in the beginning, you can just do a homography to match it. And actually that you'll see in my later parts of the talk, that itself is quite effective for some problems. Or nowadays you have very nice monocular depth estimation techniques. You take an image, you can compute the depth map for it. So you can use that to now take the ground image and use the depth to now say what the bird's eye view image would look like. Or you could have network-based techniques, right? The MLP-based techniques, transformer-based techniques, the diffusion-based techniques now. I think you would have heard about a diffusion-based technique in the previous talk. So I'm not going to talk about that. I'll tell you a little bit about transformer-based techniques. So one of the very nice techniques for transformer-based techniques was this paper called PEFFORMA, which was presented in ECCB 2022. So again, taking the automotive example, you have a vehicle, you have cameras all around the vehicle, and you're getting multiple cameras. So what you do is you're trying to learn the BEV image using the transformer, the embedding for the BEV image. And what you do is you for each cell in the BEV image, the BEV image is an aerial image and you're breaking it up into cells. For each cell in the BEV image, you're feeding it into a transformer, and then you can do self-attention to other cells in the BEV image and also to the BEV image for the time instant before, the historical BEV image. And then you can do cross-attention to all the ground images. So this is the BEV image. And now you can take the XY cell and grid it along the Z direction. And for each cell in this column, you can see which of these ground images will be visible, and you can pay attention to that. And you can, this is like a classic transform architecture. And now you can do many layers of this and use that to create a overall BEV representation, which you can then feed to other heads to do detection of objects in the scene, or to the semantic segmentation of the scene and other things. So a paper along these lines was published in CVPR 2023 called Uncertainty-Aware Vision-Based Metric Cross-View Geo-localization, where given these are different ground images, they were able to locate the vehicle on an aerial map. And not only did they locate the vehicle, they also gave you an uncertainty. They would say, this is the vehicle and this is the uncertainty heat map around it. And so the way they did it was, you take the ground images, you encode it into, you create a bird's eye view image like we talked about with the transform-based method. And now you feed it, now you're going to match it to the aerial image. And to match it, you may also solve for rotation, like we were talking about earlier by rotating it. And now you do cross-correlation between these two representations. And you use the cross-correlation to detect the peak and then also detect the space of the uncertainty about for the peak. And they were able to get nice results. You can see a big improvement from Vigor, both for locating the vehicle both laterally and longitudinally. Of course, the error is more along the longitudinal, along the road versus lateral. So within 1 meter, for instance, 96% in the lateral, but only 76% within 1 meter. Along the longitudinal, 96% within 5 meters. And these were on the Ford AV data set. So, so that was a nice result. So now, just last year, the techniques, first we talked about these matching techniques, which are matching the street view image to the aerial image by transforming the aerial image. Then we talked about how we can transform this street view image to make a BEV image and match that to the aerial image, a bird's eye view image. And now one of these nice papers which came out last year is where you can combine the two techniques. So what they do is you have the street view image, and you're going to match it directly to the aerial image. And you're going to, and they're based on the sample for geo paper, so they're going to do the info NC loss. But they also what they also do is take the street view image and make a BEV image, and then match that BEV image to the aerial image. So they're doing both of them at the same time. And they're basically taking an average of both these info-C losses. So in both these info-C losses are symmetric, you're doing it either way. And now they're taking the overall error they're minimizing is the average of both these losses. And they're able to show that they get much better performance. Remember, sample 4G was very good, and they're able to get much better performance than sample 4G. And that's what this is showing. This is the street view image. This is the BEV image, and these are just showing this. For this image, the sample 4G, the best one was the third one, and in this one, the second one, while in their case, in both, it's the first one. And they were able to show that they also collected the additional data sets. They collected data sets called CV Global, which is much bigger than the previous data sets. And they also collected data over different time. Not only they collected data across time, across years, but they were able to show much better performance, both 97% validation, 85% regional, and across continents 86. So much higher than what sample 4G was, and also across time. So the images collected at 1 year and being tested with data collected 2013 or 2019, or mixing it up. So they were able to show much better performance. So, so then I'll present my last technique on this front, and that is once you have these, for many of these problems, you want very precise location. And to get the very precise location, if you're trying to match the if you're trying to transform the satellite image to match the ground image, you don't get that. So the intuition is you'll get higher precision by trying to convert the ground image to look like the satellite and then match that. And the area where you have most of the information to do that is the area often which is nearby in front. So what this technique does is it just does a simple homography to convert this ground image into a BEV image. So this homography will be accurate more. It's actually using a spherical transform to do it, but it will be accurate more just near the ground, because they're not using any 3D information. And they're going to match that to the satellite by homography. And so this is the overall technique. And now it's very interesting. Before deep learning, the best papers for doing alignment, if you really wanted really high precision alignment, you would use what are called direct methods. In my company at SRI, we were famous for doing pyramid-based direct methods, where you would align the two images together, actually trying to walk the two pixels over a pyramid and trying to really make sure all pixels align to each other. So these set of techniques are now coming to that, but using deep learning. So what you do is you take the ground image, you convert it to a spherical image, basically what you're calling a BEV image. You run it through these neural networks to come up with representations for each one of these images. And now you're going to do a correlation between the two feature maps. You're only sitting in a local area. You know you're within 15, 20 meters. Now you're trying to search and get it down to within 1 or 2 meters. So you do that over multiple representations. You have a hierarchical representation of your feature space, and you do the correlation. You find the peak. To find the peak, you use a small MLP to predict it, and then you calculate the homography based on that. You're actually predicting. You take a bounding box and you're predicting how each of the corners of the bounding box move to calculate the homography, and that's what the MLP is predicting. They use that new homography to walk the image, and then they do the process again in an iterative manner. So you're warping the one of the images, getting it closer, and then you're doing it again. And they're able to show that they, are on the WIGOR data set, they're able to localize the images to within 2.7 meters mean and 1.18 meters median, and orientation with about 2 degrees for same area. So if you train in one area, test in the same area. If you do cross area, they're about 3.46 and 3. So I think you need a combination of these techniques. I spoke about the technique which took sample for G, but it made it go did it multiple ways. That's good for getting you what you call closer to get you close, and then you use something like this to get you to do the final alignment. Okay, and these are some of the examples from there. So I only have 4 minutes left. I don't think I have time to talk about it. I will include it in the slides so you can see. But if somebody has a few questions, I can speak to it. I can answer.
So I have one question. So for the last talk, you mentioned about the homography mapping. So do you know like how many iterations it's gonna achieve the best, and how is the complexity for the recurrent homography estimation?
I don't remember the number of iteration. I don't think it's very complex. I think you can do this at a really high speed because you're just doing it locally.
Yeah, and also regarding this one, so if I increase the ground as an aerial image, like let's say bigger is 50 by 50 meters.
Yeah.
What if my start space is like 100 by 100? Do you think it's still like have a ratio of like how?
Yeah, no, I think because you're using a hierarchy, so just like the pyramid-based method, you're doing from post to find. So you can still use that to search for it. Any other questions?
I think I have some. Yeah. So, I want to go to the second one.
Oh, I can go to the second one.
Yeah.
Okay. I can go to that very quickly. Okay. So the second set of techniques, and these are more classical techniques. Is suppose you in the techniques we talked about before, we were assuming we don't have any 3D information in the reference. But and the reason you assume that is because getting 3D information is much more painful. People do have it, but for somebody just searching on the web and saying, okay, I'm downloading Google Maps, it's easy. It's more work to be able to get 3D reference everywhere. So the one of the first techniques we developed at SRI, this was about 5-6 years ago, was skyline matching. And so you have an input image, and we were using this for both augmented reality from vehicles kind of applications. So you have an input image, you can do semantic segmentation, and you can actually discover the skyline, right? And now you can use that skyline to actually match to the reference. And that's what you're seeing over here. We assume in the state of New Jersey has LiDAR collected all over New Jersey. So I can download this LiDAR map, and now I'm driving in Princeton, and I'm matching, this is the ground image, I'm doing semantic segmentation, I'm getting the skyline, and I'm matching that to the skyline which I'm getting from the LiDAR. And from that, I can calculate the orientation very accurately. And this is in a rural area where there are no buildings, but I'm matching to tree lines. So if you have this kind of data, right, this problem becomes a lot easier in places like this. Another set of techniques related to this, and this is developed by one of my collaborators, Ram Jun, who's at OSU, is the same thing where you have, so in all the previous techniques we were talking about, we were saying you only have a panorama, one ground image. But now if you have video which you're collecting from the ground, now you can use that to also do the matching. And what they're doing is you have the street view images, and from the street view images, they are detecting building segments from them. From the aerial data, also they have extracted building segments between 3D and recovering 3D. And now you can both recover point clouds in a continuous fashion from the ground images. You have point clouds you've already constructed beforehand from satellite data. You can match those point clouds to each other. You can match building segments to each other and do a bundle adjustment. And then they have a full pipeline which you can put into a SLAM kind of method to do this in real time. And there's a nice video which shows it over here, where this is driving around Columbus or Ohio around the OSU campus. They do semantic segmentation, they get the building mass, they do the point cloud reconstruction from the ground SLAM, and now they're matching those, both the 3D points and the outlines of the buildings to the other one, and they're able to locate themselves quite well without GPS. So if you have video and you can recover 3D from the video, then you definitely can use it. Similarly, if you had a problem in a lot of these autonomous cars, they have LiDAR. They're getting very rich 3D. And now you get 3D from the air, so you can definitely use that to match too, right? Okay, so that was my final segment, which I spoke about.
Thank you very much.
Thank you.
I think we can have one question. I can ask a question for the CD global one.
Yeah.
So this is kind of a power of the data, right? More than the algorithms themselves.
Yeah.
Do you think that the field now is, from you reading in the historical way,
yeah.
Do you think we are now going to have a global scale for cross-image localization and try to solve this in global wise, more than just city wise?
So there are two different answers to this question. So first is there's another whole body of work where given any image, just a regular image, you're trying to say where was this image taken, right? There's a GeoGuessr game. There was a paper last year in CVPR. Those techniques work to locate you, but they'll say, okay, this is an image taken in New York City, or this is an image taken in New Jersey State, right? They only work at that scale, right? And so there's a whole bunch of papers like that which are not finalized. Then there's the second one where I want to know where I am within a centimeter ultimately, right? Or within a meter, right? So that's a very different problem than the GeoGuessr game, right? For those, you do need to, if you're matching to reference data, you would need reference data to locate yourself. You do need this global reference data, right? The problem would be very different, as I talked in the beginning of the talk, depending on where in the world you are. It's a very different problem if you're right here outside this hotel than being in the center of Tucson, right? Or being in Vermont, where you're seeing beautiful green mountains, than in New York City. So it won't be one technique; it would be like a family of techniques. So it's almost like I think in the future you're going to have some agentic AI system which is going to look at the image and say, "This is the set of techniques I want to use for this image," and then solve it, right? You would need to build these models based on where you are, but the model would also vary. I don't think it's going to be. My hunch is it's not just one technique; it's a bag of techniques, depending on where you are and how the problem is focused. And it's much more challenging also when you have a limited field of view. Up to now, many of these things have been assuming you have 6 cameras around the vehicle. But imagine the augmented reality problem. You just have 2 cameras here, right? Or you may have a little more, but you're trying to locate yourself outdoors anyway.
That's going to be a good discussion for the panel, right?
Yeah.
You're going to be with us, right?
I'm sorry, I worked with that.
Okay. So we might discuss it in the end. Thank you very much. Really appreciate it.